Hi guys, today we're going to learn about the p-series test. A series of the form the summation from n equals 1 to infinity of 1 over n to the power of p is called a p-series, where p is a positive constant. A special case that is very popular of the p-series is going to be when p is equal to 0. The series is going to look like the following. And that it's equal to 1 to infinity with the summation symbol 1 over n, and this one, when we expand it, it looks like this. It's called the harmonic series. The integral test can be used to prove the p-series test. We're not going to a formal proof, but let's look at the p-series that were in yesterday's notes and last night's homework and see which ones converge and which ones diverge. Maybe we can get the conclusions of the p-series test. So the first one that we have is the harmonic series. The harmonic series is this one, where you have the summation from n equals 1 to infinity of 1 over n. If you cannot predict that one because it's the first one, let's do it like step by step. So you have that this is your harmonic series. And you know that, well, the most natural test to use here, it would be the integral test. Okay, so you would have 1 over x dx. When you take this integral, this is going to be the limit when c approaches to infinity of 1 over 1 to c of dx over x. So if you do this, you know that that integral is going to be equal to the limit when c approaches to infinity, and you know that it's going to be natural log of absolute value of x evaluated from 1 to c. When you evaluate the situation, what we have, let me show you over here, you have that it's going to be the limit when c approaches to infinity of natural log of absolute value of c minus natural log of 1. So what you can see here is that this one, obviously it's going to be 0, but this one, it goes to infinity. So you can conclude that this is going to be infinity. Thus, okay, the series, the harmonic series that you have, okay, you can conclude that it diverges, okay, by the integral test, okay, by the integral test, okay. So with this being said, we can conclude, and we can put this one over here in the diverging section, okay. So this one diverges, okay. Now you see this one, check. Now this one, what's the business for that one? That one, if you do the same idea, okay, we also do the integral test to prove it. So you have something like this. So you have that the integral from 1 to infinity of 1 over x squared dx is going to be equal to the limit when c approaches to infinity of what? The integral from 1 to c of dx over x squared. Okay? So what you have here is that this is going to be equal to the limit when c approaches infinity, and you have that this is going to be equal to negative 1 divided by x, okay, and then you are going to evaluate from 1 to c, and this is going to be equal to the limit when c approaches to infinity of negative 1 divided by c plus 1, okay. So this one, you can see that it's going to be equal to 1, okay. Therefore, you can conclude that thus by integral test, okay, this is going to converge, okay, converges by integral test, okay. So you can see that this one converges, so we're going to put this one in the convergence section. Okay, so now you can see, kind of like, you can start seeing the pattern that we have. What's going to be the business with this one? This one is going to converge, okay. So you have this converging. What's going to be the business with this one? This one is going to diverge. Yeah. What's going to happen with this one? This one, you can have that the exponent is 3 over 2. So that one is going to converge because the exponent, technically speaking, is 3 over 2. Okay? And this one over here, what you have is the summation from n equals 1 to infinity. You have 1 over n power 4. Okay, so that one is going to converge as well. So you can see a very fun pattern here. You can see that if the exponent is greater than 1, it's converging. If it's 1 or less, it's going to diverge. So guess what? That is going to be the P-series test. So a P-series, the main thing is that it needs to look like this. So the first condition is you know that the series is going to converges if P is greater than 1. Now it's going to be divergent, okay, diverges, okay, if the P is between 0 and 1. And if you have the harmonic series, is going to diverge as well, okay? So that's what we have for this equation. Now let's go over 2 examples that we have over here. Determine whether the following series converges or diverges. Okay, so let's look at this one. This one, you can see that this is the same as seeing n equals 1 to infinity of 1 over n to the power of 1/3. So you can see clearly that this is a P series immediately as we spot that one. Okay, moreover, you know that the P is going to be equal to 1/3, which is less than 1. Okay, so since it's less than 1, you know you can conclude thus, okay, your P series, this one, okay, what's the business of that one? It's going to diverges, okay, by P series test. Okay, so isn't that simple? So that's what you have for this one. Let's look at the last example that we have for today. You can spot, this one is more clear-cut for my taste. You can spot immediately that it's a P series because you don't have a square root or a root or nothing, okay? This is clear-cut that you have a power of 5 over 4 in the end. Okay, so you have that it's a P series. Your P is going to be 5 over 4. You have that this one is greater than 1. So you can already be thinking, oh, this is going to converge. Yes, you're right, okay? So your conclusion here is thus, okay, my series n equals 1 to infinity of 1 over 5 over 4 converges by P series test. And that's pretty much it for the P series. I hope that you find this test very helpful and easy. Bye!